Welcome everyone to episode 19 of Games with Go, where we're finally going to start evolving our abstract picture trees. So last episode we got the basics of a graphical user interface going, where we laid out our random abstract picture trees and turned them into image buttons and made them selectable. So what we're going to do tonight is implement crossover and actually start making them evolve. So what is crossover? So we're going to have the user select some number of trees that they like. So say they selected 3. Then we're going to have to build new trees to fill up the grid again, right? So here we've got 16 trees. So from the population of 3 that the user selects, we need to make 16 new ones. And so the way we're going to do that is we'll take pairs of trees, or potentially more than pairs, and combine sections of them. So for instance, you could randomly pick this node here and this node here and make a new tree by replacing that node with this one, generating a new tree that shares some aspects of one of the user's selections and some aspects of the other user's selection. The idea being that if you saw an image that maybe had some shapes you liked and you saw another image that had some colors you liked, some of the results might end up having both the shapes and the colors you like. Thereby gradually the user can make pictures look, more and more like whatever they want to see, whatever they think is coolest. So before we start on crossover, there's a few bugs I noticed after last episode's stream that we should fix. So the first is in the GUI package. Just some bad capitalization in the mouse state struct. Button should be capital B. And then we have to go down into update, make it match. And image button as well. And I think that's it. I don't think this other file has any reference to it. Nope. Okay. Next little bug. When we're doing our masking of the button mask to the mouse button state from SDL, this should be an AND, not multiply. I think I just hit the wrong key last time, but it happened to work for left button, but it doesn't work for right button. So change that to ampersand, and then mutate. So this should be the lowercase. And that's it. Okay, so now we're going to head over to the abstract picture tree package, and we've got to add some more stuff here to be able to do what we want to do. one thing we need to be able to do is to be able to copy a tree. The reason for that is if we just were to like take the pointer to this node and stick it onto another tree, you would end up with multiple trees sharing the same subsections. Now that might be nice in terms of sharing memory, but it means that if we were to then mutate one of these nodes, that it would mutate potentially all of the other trees nodes. Basically be a big mess. So when we get go from our surviving trees to a new population of trees, we want them all to be completely new trees, complete copies, not sharing memory with any of the old trees. So we need to make a copy function for a node. So how do we do that? Let's call it copy tree. And then we'll take a node. We're going to end up needing a parent, and we'll see why. And we're going to return a new node that's going to be a copy of this one. So by choosing to use an interface for nodes, it makes the copying step a little bit tricky, but there is a way to do it with something called reflection. And at a high level, what reflection means is when a, is it not called reflection? Oh, reflect. It's when a program can kind of look inside of its own types and ask questions about them. And you can do things like see what type something is at runtime. In some languages let you see what name a variable is at runtime. Things like that. So what we need to be able to do is given our node, we need to be able to see what kind of node is actually inside of it. Remember, we have all these different ones like op-lerp, base node, op plus, and so on. And so the way that an interface works in Go is there's actually two parts. So an interface is two parts. One part just says what is the type that the interface is containing, in this case. And then the next is the actual thing it's containing. So this might be like, say, our op plus node. And in this case, it'll have a pointer to it, a pointer to that actual data. So given that interfaces sort of internally know what they are at any given point in time, we can use reflection to ask. And we're going to need to know that because we need to make a copy of the particular type of each node. So what we can do is we can say so this here will take our node and figure out what type it is. Figure out if it's an op plus or an op sign or an op fractal Brownian motion and so on. And then we can use reflect.new to make a new one of that type. So we're making a new node that is an op plus. But then we want to treat that node. We basically want to wrap it back up in a node interface so that we can use it just like a node. So you can do that by calling a function interface and telling it that the type of the interface is node. This is a cast type, or a type cast that says this interface is going to be a node interface. So it's a bunch of confusing mess, but in the end, we have a typo here. This is a function. In the end, we have now a copy of this node that was passed in, or we have a new node of the same type as the one that was passed in. But it does not have any of its values filled in. So like its parent and children aren't set at all yet. It's just a blank node. So we need to set those things. So we need to set the parent. Do we have a set parent? Yes. Set the parent to the one that we passed in. That's why we needed it. Why do we need that? Why can't we just call node.parent? We'll see. Then we need to set the children. So we need to make a whole new array, or a whole new slice, to hold the children in. It'll be the same length as the slice as the children's slice of the node that we're copying. So we get a slice ready. And then we set the pointer to the children to our new slice. And then we use, once again, the magic of recursion. Because we don't want to copy just the node we have, but the entire tree. So all the children and their children and their children and so on. And here we see why we need the parent, because when we copy the children of this node, the parent needs to be set the parent needs to be set to the copy, not the old node, not the original node. Why is this not happy? Oh, we don't have a set children, so let's make a set children. This will take a slice of nodes. And then we just say node, children. Very simple. And then when we're all done, we just return the copy. Okay, so now we have a function. We can pass it a node, any node we like, and it'll give us the entire tree underneath it. So we could pass it this node plus, and it would give us back the plus, the 5, and the y, a distinct copy of it. Okay, so now the function to do crossover. So I'm going to call it replace node. Make it a little easier to understand. So the idea is we're going to take one node and replace it with another node. Old node gets replaced by new node. So the first thing we're going to do is take the old node's parent, and we'll just set that equal to a variable for convenience. And if the parent is not nil, so what we need to do here is whatever node is being replaced, we need to find its parent and figure out which child points to it, so that that child can now point to the new node, right? That's how we're going to wire it up. So if we want to replace plus, we have to go up to its parent node and see which child points back to us, because we're going to replace that with a new tree. So we can just iterate through all of the old parent's children. And if the child equals the old node, if it's the same thing, and in this case it would be like the same pointer because it's an interface, then we will now set that child to point to the new node. And then the only other thing we have to do is set the parent of the new node to old parent. All right, so we wire up the parent to the new child and the child to the new parent it's going to. And that's it. That's going to let us be able to do crossover with our trees. That's the basic operations we need. So let's go back to evolvingpictures.go. And what we're going to need now is some kind of button we can press in order to fire this off, in order to start the new generation. So to do that, we can use our image button that we created last time. And one way we could do it is like load up a button icon or some kind, but we're just going to do a really quick and easy way to make a button, some programmer art. So we're going to do a little trick. We're going to make a function that just returns a texture that is a single pixel. Of whatever color we want to specify. And let's see, do we have our texture? So I'm going to go to pixels to texture in evolvingpictures.go and just grab this, because we're going to use almost the same code. Then back to GUI. So make a new texture. So I'm going to change this from streaming to static, because we're not going to modify this texture. And the width and height of the texture are just going to be 1. Very easy. Then we need to make our pixel data. It's a single pixel, so we only need 4 bytes, 1 for each color. Then we update with the pixels and the stride length, which is just 4. Then we can return that texture. So that's going to let us get a single pixel texture of whatever color we want, which will let us make really simple buttons. Okay. So how do we do that? We will need to grab that texture, pick a color for it. I'm just going to do white, but you can do any color you want. Then we need to define a rectangle for it, which is where we're going to draw it on the screen. So we're going to take, we want to center it. So we're going to take the window width over 2 minus the pick width divided by 2. We're going to make the button the same width as the pictures are. So that'll be our X. And then for Y, we're going to want to put it down. I'm going to put it down towards the bottom of the screen. So we'll take the win height. Now we put it at the very bottom if we just put it at win height. So we'll subtract a little bit. We'll just subtract 10% off of the bottom of the screen. And then the size will be pick width and then we'll make the height a little bit narrower than our pictures. Again, we'll do it as a percentage of the window height. So doing things always as a percentage of the screen size is a little bit annoying and confusing, but the benefit is that no matter what screen size someone chooses, or if you want to allow resizing, things will still look correct within reason anyway. Let's see, what's wrong here? Okay, declared not used. That's fine, we're gonna use it. So we've got a single pixel texture and a rectangle for where to draw the button. So now let's make the button. Pass it our single pixel texture. And the selection color, which won't matter because this won't ever get selected. It's not going to do that. Okay, now we have an evolve button. So now we need to draw it and update it. So let's see, we should probably do that at where should we draw it? I think it doesn't matter. I think that'll be fine. Oh, we gotta pass the mouse state. This probably needs the renderer. Okay, one last thing we need to do. This should be evolve button text. Is we need to make the pictures draw not quite as far down as they have been. So we're going to change this 0.9 to a 0.8 for the picture height to make them a little smaller to make room at the bottom of the screen. Let's see what we get. Okay, we've got a button drawing. Just a white square programmer art for now. And we can check and make sure that if we change screen sizes, that it still works. Still draw something sensible. Okay, everything just gets smaller, so that's good. Go back to big. Okay, now we need to make our button actually do something. So let's check to see if it was clicked. So if it was left clicked, what we'll want to do is we need to build up a list of all the pictures that the user has selected. So we'll make a selected pictures slice. Start it out at length 0. It will have pointers to pictures. And then we're going to iterate over all of our buttons. And if the button is selected, then we will append to our selected pictures the corresponding pic tree that goes with that button. Okay, so if the button gets clicked, we make a list of all the images that have been selected so far. And then probably want to check if the user has not selected any pictures, then we probably want to, I don't know, break out of here. Well, let's just see. We only do something if it's not 0. Okay, so we're going to make a new generation. So one thing we got to do is clear out all the buttons. And then we're going to want to evolve things. So evolve is going to be a bunch of code. So let's make a separate function for that. Let's go up to near where we did the mutate function. Okay. So evolve is going to take a slice of the survivor pictures, and it's going to return a new slice of pictures, which will be the new generation of picture trees. So let's make a new slice. And we're going to use numpix because it's going to be the same size as the initial population. And then one thing I want to do is I want to make sure that every tree that the user selects, so if they select 3, I want to make sure that every tree that some part of every tree ends up in the next generation. So we could just pick pairs of random trees to combine to make new ones. But then if you are unlucky, there might be a tree that the user selected that doesn't make it into the next generation. So I want to make sure that that doesn't happen. So I'm going to go in 2 steps. So first I'll go from I is less than the length of the survivors. Survivors should be plural. Start I at 0 and go up to the less than length of the survivor. So we're going to iterate through every survivor picture at least one time. And then we're going to say we're going to make pick our two trees to combine. So the first one will be survivors of I, right? So A will guarantee that we get at least one instance of every survivor in the next generation. And then B we will pick randomly. So we'll pick a random integer. From the survivors array. And you may notice here that A and B could end up being the same tree. That's okay, we're going to allow it. You could have a tree do crossover with itself. That could be interesting, so we'll see what happens. All right, so now we need to do crossover. So we're going to make another helper function. So what we're going to want to do here is we're going to get like a new tree equals cross between A and B. Now we have the basic function we need for that in here. Oh, not GUI, in here. Replace node. But we need to do it to a picture, which remember has 3 trees to it, red, green, and blue. So we're going to make another helper function, which will take 2 pictures and return a new one. So the first thing we're going to want to do is we're going to want to get a copy of A. So we can use our handy copy function. So remember, a picture has 3 nodes. So we're going to copy all of them. So we're going to make a new picture struct. We're going to copy A. And since this is the root of the tree, it has no parent, so we'll pass nil to copy tree. Green. Blue. All right, so at this point, a copy will be a complete copy of this whole tree, right? Of this tree we selected. Okay, then we want to pick a random node of the 3 start nodes. So we'll say I think we do this in mutate already. So it's going to be this same logic. You know, we could actually make this a function too. So let's do that. Let's make a pick random random color, returns a node. This will operate on my picture. And we'll just say, get a random number between 0 and 2. And we'll return either the red, green, or blue tree for the picture. Okay, so we will pick a color from the A copy tree. And we will pick a color from the B tree. And then from the tree, we need to pick a random node in it. That'll be our crossover point for each. So we'll say, we need to figure out how big the tree is. Oh no, we can get this. We'll get an index, a random index into the tree by getting a random integer between 0 and how many nodes are in the tree. So this will be our index to a random point in the A tree. And then we can get that node by calling our getInth node function we wrote. Give it our index. Okay, so at this point we've got a random node from the copy of the A picture. And then we'll get a B index. The same way. We'll get a B node. Same way. Now at this point, B node is what we're going to take and splice in to the copy of A. So we want to make a copy of this as well. So we make a B node copy equals copy tree and now we have our two nodes, both are copies. So we can call replace node, A node, B node copy. And then once we've replaced a node in the copy of the A tree, we can return that copy. So this should do our crossover. So now we can say new pics of I equals cross of A and B. All right, that's great, but if the user only selects 3 survivors, we're only going to have 3 pictures so far, so we got to keep going. So here we do until I, as long as I is less than the length of the new picture array. All right, so we're just filling in the rest of the new picture array. We're basically going to do the same thing. Oh, we need to do I++ there. Except this time it'll be random pairs of trees every time for the rest. Okay, so for now, let's just do that. See how it goes. What's this unhappy about? So now we can say, what do I want to call evolve? Okay, yeah, so we'll call, so this is our original, picture trees. Slice. So we're going to replace it with the new slice we get from evolve. And by the way, an easy way to get a bug in Go, if you accidentally do that, this will be a different pick trees than the one outside of the scope, and it won't do what you think. So don't do that. Okay, so we're replacing our old array of picture trees with the new one that we got from evolve. And now we have to fire off Go routines again to generate images for all of them. So we call our tree to pixel converter. And our channel's still set up, still ready to use, so we can just keep using it. Let's see, APT to pixels. Oh, APT to pixels no longer needs a renderer because it only returns a byte array. So let's get rid of that. We can, the initial time we used it here, we can get rid of that as well. Pixel result, not plural. All right. I noticed some errors up here. Oh, we need to return new pics from the evolve function. This needs a default case. Which should be an error. That should never happen. All right. Shall we see what happens? Okay. So testing the case of not selecting anything, nothing happens. That's good. So let's pick two things that'll be easy to sort of tell if they combined or not. Or three things. I'll pick this, the red, and the blue. All right, it's looking like it's making sense. So we're seeing here images that have properties similar to the ones we selected combined. So if I take a blue and a red, evolve, we get some more that are just blue and red, but we get some new things too. So what if I combine, this looks like it has some noise in it now. All right, you see how you can keep kind of going deeper and deeper, getting new stuff. So if your favorite color is purple, you do only purple ones. Now we get mostly purple ones. All right, so it looks like it's working and kind of doing what we'd expect visually. Now there's another aspect we can add to this though, which is mutation. And we already have a mutation, a mutate function that we set up before. So that's all ready to go. So this should be pretty easy to add. And the mutation, what you can do with it is you can kind of tune the rate you want to do. So you could do tons of mutation or only a little bit. So let's just say we want to do a ton of mutation, so it'll be obvious if it's working. We'll do 20. So this is going to mutate every picture 20 times. Or between 0 and 20 times, because this is random. So I will be less than R. So we'll call pick.mutate. Range. Okay, so for each picture we pick a random value between 0 and 19 and mutate it that many times. So what we should expect here is even if we pick say two kind of simple looking images, we should get some new features. And sure enough, we see all sorts of like new stuff coming in. In fact, a lot of them aren't even recognizable as the pictures we combined before. So that's like the rate of mutation is something you might want to tune such that you get new interesting features some of the time, but you don't totally obliterate the look that you were going for when you were selecting things. Another thing we can do is you can also play with how big the trees are. And that might influence what the mutation rate you want to choose is. So let's do some more playing. Let's look what happens if we just do this green one and have it cross with itself a bunch. So you can see sometimes, even though an image looks really simple, the equation is usually pretty big behind it. And so sometimes with minor changes, interesting stuff can result. Like it's getting pretty wild pretty quick. Okay, a couple of things we can do. We'd like to be able to see these images larger, because right now all we're seeing is thumbnails. And also, I don't know if you can see it on the stream, but you can often see jagged edges on these thumbnails that don't look so nice. So there's an easy trick we can do to get free anti-aliasing. And let's see. I think all we need to do rectangle. Yeah, I think all we have to do is if we double the width and height of the images we're making, because we have the render scale quality hint set to 1, we'll get bilinear filtering for free when STL shrinks it back down to the actual size we're rendering it at. You do it here too. So I'm going to run it real quick. Something bad has happened. Oh, we need to do it here as well. So both when we render the tree and make the texture, we need to make it double size. There we go. Yeah, and it might be hard to see on stream, but if you're looking on your own computer, it is less jagged when there's lines now, which is cool. I kind of like this one. That's pretty cool. Okay, we got time to do one more feature, which is let's make it possible for the user to right-click on a thumbnail and get a full screen version of the picture so they can really see what it looks like. So to do that, we're going to keep track of kind of the state of our program. Right now it's just going to have one state really, so it'll be pretty simple. So we're going to keep track of whether or not we are zoomed in. And then if we're zoomed in, we're going to keep the image we're zoomed in on in here. So just before our main loop, we will set our GUI state to not zoomed in with no zoom image. And then in here where we're checking to see if we're left clicked, we will also check to see if we were right clicked. And if we were right clicked, we want to make a larger version. So we'll get zoom pixels from the associated picture tree. And we'll do full screen. And again, we'll do ×2 for some free anti-aliasing. Poor man's anti-aliasing. And we'll get our texture. Else if we need our eye. For eye button, okay. So we'll set our zoom image to the zoom texture. State.zoom equals true. And then we only want to render all the buttons if we're in the not zoomed state. So actually we're going to go higher than that. So if we're not in the zoom state, do all of the drawing stuff. Else, and for now, the only thing we want to do in the zoomed in state is see if they right click again. And then we'll flip the zoom state back equal to false. So let's see how it goes. All right, let's get a cool looking one to zoom into. I like this. All right, I kind of like this one. Okay, so I'm going to right click on that one. That's going to take a while because it's twice the size of 1080p, or more than twice as many pixels actually. We forgot a step. We got to actually draw it. We're doing full screen, so source and destination are both nil. So we just copy the whole zoom image to the screen. Let's try again. Let's find a good one again. All right, let's try zooming in on this one. So right-clicking. There we go. So now we get a nice, mildly anti-aliased full screen picture. And we should be able to right-click to get back out. Yeah. This one's kind of cool. All right, so that's going to be all the stuff we're going to add tonight. I have some homework ideas. One of which you'll notice is right now when you right click, there's a long pause and then it pops up. So what we should do is that should happen on a background thread, and we should show some sort of loading indicator. So, homework ideas. Okay, and this could be any kind of indication you want, any kind of thing you can think of. It could be a little spinner or something. Another thing we could try is the way that we are rendering our picture trees right now. If you go to the picture tree package, is we're doing these series of eval calls with X and Y. So for every pixel on the screen, we're calling eval for every single node in the tree, which could be 25, 30 nodes at a time. And that's really expensive for a few reasons. For one, we're passing X and Y onto the stack over and over and over. But we're also hopping to different nodes in memory. And those nodes are not contiguous in memory. And when you hop around like that, if you miss the CPU's cache, it takes a long, long time to get your data. So we could potentially be missing the cache a lot. So one way you could make this faster is instead of processing X and Y every single time, you could instead pass in an array of float 32s. And then each node will process the entire array all at once. So you only have to traverse the tree one time. So instead of passing X and Y for each pixel, pass a single array for all of the pixels and evaluate the whole array at once. And if you get that working, measure it to see if it actually made it faster, and if so, how much faster it made it. I suspect it will be a lot, but I have not tried it, but it could. Something else you could experiment with, if you get ambitious, is currently we have a set of string functions for each node that outputs this sort of Lisp-like syntax that represents the equation. But this could output it in any format you want. So something you could try is make these string functions output valid Go code and make a program that will run that code and render it. So the idea here would be you can make a template source code that will render. Let's see. Yeah, so it'll have all the SDL2 setup, kind of like we're doing in here, and then so that could be anything. You could just use $. And then you can take the output and replace the $, with your equation. Right, so you'll basically take your template program that's got a $sign in it and replace that $sign with the output of your string function, which will give you a really long Go function that you can then run to draw the picture. And that will be really fast because it's not having to do any tree traversal at all. It's just going to be executing Go code. So this is a kind of big project, but it's kind of neat. People call, you call this meta programming when you do this, to write one program that outputs another program, and it's pretty fun. So if you find this stuff pretty easy and want a challenge, this is hard but fun. These will be a little bit tricky too, but it'll be good practice. All right, any questions before I sign off tonight? I will hang out for a little bit and evolve some pictures. If anyone has questions about this stream or next stream, just let me know. And remember that if you subscribe on Twitch, you get no commercials, and also you get access to the source code repo, which has a release for every episode we've done. So it's easy to follow along, even if you're behind. Thought of one more homework you can try. Currently, we have a red, green, and blue tree for each picture. You could try variations on this. You could do a grayscale picture with just one node, or an HSV picture, which uses hue, saturation, value for the three trees. And you can convert an HSV values to RGB. You have to Google that. Macrono in chat asks, hi, what are you making? We are making a program that lets you evolve pictures. You start out with random pictures that are generated by a tree, which represents an equation. And you can pick ones you like say I'll pick this green one and this purple one. And when you click the button, it'll generate a new set of trees that combines parts of each picture, each part of the picture's equations, into new ones, simulating the process of evolution. And crossover being where you take one part of the tree and graft it onto another tree. it is not averaging the images. So the images are represented by an equation tree. So for example, it could be 5 plus y minus x could be an equation that you run for each pixel for each pixel on the screen, right? So for 0, 0, you do 5 plus 0 minus x, and that is the color of your pixel. So these trees can get very big, and we have lots of different functions they can be: division, multiplication, noise functions, stuff like that. And then so when you've selected some trees you like say these three, you can then do crossover, where you can take some part of a tree, like say this part of this tree, and stick it onto a part of another tree. And so the resulting tree will have part of each old equation combined into a new equation, and you get a new picture. And if you watch, you'll see how if I pick, let me start from scratch again. You'll see how if I pick one, like say this blue and purple and this red one, that some of the results look like visually some combination of the two. You can get features from one added to the other. Does that make sense? And there's also mutation too. So nodes can just randomly change occasionally, giving you entirely new features. By features, I mean shapes that you see in the images, right? So like this curve here is probably being generated by one area of the tree. So if I pick that and this, we might get some of these like cloudy shapes along with those shapes. These images are being generated by random equations. And in fact, if you want to get a lot more detail, if you check out the previous 2 or 3 episodes, you can see all of this getting done from scratch. But the basic process is we have a bunch of different functions like plus, minus, multiply, divide that are nodes in a tree. And we generate a random node, add it to a tree, generate a new random node, add it to the tree, and so on up to like 20, 30 nodes, which gives you the equation. And then, let's see. Then we iterate over each x and y value on the screen and evaluate the entire tree to get our red, green, and blue values for each pixel. Yeah, so we can print, let's see. I'll do this on right click. So when I right click, I will also print. Not here, here. And then I'm going to make the trees a little smaller because otherwise it's kind of hard to read them. So the images will be a little simpler. What do we do? Oh, we can't do that. Okay, so this blue image here, for example, I'll right click on it, get a big view, but that also will now print out the equation. So the red pixel is the red value of the pixel is represented by this equation. The green value of the pixel is represented by this equation, and the blue by this one. And you can see how x and y are variables in that equation. So we run this equation for every single pixel on the screen with each x and y value, get the results. Chat is asking if we could take an image as input and then generate an equation that would draw it. And no, definitely not. I mean, in theory, that would be possible, but this program doesn't help you do that at all at this point. What you could do, though, is this evolution process that we're going through manually, where a user like picks the images that they like. You could use some sort of comparison function, a function that compares each of these random images to the Mona Lisa. And the one that looks most like the Mona Lisa, or the ones that look most like the Mona Lisa, would get selected automatically. And you could run that again millions and millions of times, and you might get something that looks vaguely like a Mona Lisa. I don't think you would do too well, but it could happen. So the equations get mixed, like I said, because they are trees, and you can grab any subsection of a tree and graft it onto another tree. And currently that combination just happens randomly. We pick a random node, yank it off, pick another random node, and attach it there. And we just do one crossover per tree right now, but you could do any number you wanted to. And then on top of that, we have random mutations that can happen. So a node could just randomly change from a plus to a minus, for instance. All right. Oh yeah. We're doing one last homework. So yeah, instead of doing RGB based trees, where it was an equation for red, green, and blue, you could have an equation for hue, saturation, and value, convert that to RGB. You could do grayscale, which would require just one tree. Just the intensity of the pixel will be done by one equation. And you could do black and white, which also would have just one node, and you would pick a threshold, like if the value is less than 0, it's black, and greater than 0, it's 1. So there's lots of fun experiments you could do with this. You would get very different looking pictures with each one. Chat asks if a plus node can have a minus child node or any other symbol. So no, that's okay. So I'll show an example. So say we started building a tree and we picked as the first node a plus. Okay, so a plus has two children because you always add one thing to another. And if you want to add a minus as a child of that, that's fine. That would be a minus. And let's say this was x. And then let's say this minus also has two children. And this could have, say, an x and a y, or it could be anything. So the equation that would be, in the end, is x minus y plus x. So the only thing you have to assure yourself of is that the leaf nodes, the ones at the bottom of the tree, here, here, and here, that those need to be either x, y, or a constant. So that's the only kind of logic we have, is at the bottom of the tree are ones that have no children. All right. So yeah, if you've just tuned in today, you can go back to, I think, episode 15 or 16 is where we started this project and kind of see it all happen. Gotcha. Okay. So this can give you lots to do. What we're going to do next episode is I think we're going to start out being able to output an image that you like to a file in a format like this, and then try to be able to parse this text and recreate the tree. So it'll sort of be a parsing lesson, and it'll also let you like permanently save one of these images so you don't just lose it when you close the program. Macrono is asking if we can see some more images. it's getting way past finish time. But if you look on my Twitter, I've got a few I've posted that were pretty cool. I'll do a little bit more. So now you can see like there's a lot with this feature with the vertical lines. And if I like pick some, say I don't like that, and I can just pick two that don't have it, and they're gone. This one looks pretty different now. Yeah, and sometimes there'll be a picture that's just nothing but blue, but the equation behind it is actually really, really big. Oh, you know what, guys? We've got a bug. Let's fix it. I forgot something. There is a special case in CopyTree. So for the most part, all a node needs is its parent and children set, but there's one that is special. So we're going to do a type switch, which is like a switch statement, but just for the type. So we're going to look at what type node is. And in the case of op constant, we need to set the value because op constant has a value. It's unique in that way. So we'll set its value to the node's value. I noticed down here that all of our constants were 0, and that's why, because we weren't copying it. I think that will fix it. Let's try it. Maybe we'll get some nicer stuff. All right, that's interesting. I like these three. Yeah, this is nicer looking. We were losing some detail. So now if I right click on one of these, yeah, we see the constants are back now. Getting weird. Let's do a new one. I like these because it kind of looks like a three-dimensional. All right, I gotta go, everybody. Thanks for tuning in. Next episode, we will save these equations out to a file and parse them back in so that we can save our trees in a very, very small format. This is much smaller than the image would be. Good night.